Okay, in this problem here I have a chain that consists of 7 links, each having a mass of 0.112 kilograms. The chain is being pulled upward by force applied by your hand to its top length, giving the chain an upward acceleration of 2.85 meters per second squared. Find the magnitude of the force that each link exerts on the link below it. Alright, well, if you have a problem like this, what I recommend is we're going to start here at the bottom. I'm going to draw a free body diagram. Again, that's pretty much the key to all these problems. So if I do the free body diagram of the bottom one, I would have draw myself a dot. I have a force coming down here, and a force coming back up here. Let's see, get these to line up right. Now I'm going to go ahead and label these chains too first. I'll make this C1, C2, C3, C4, C5, C6, and C7. So this would be the force that C, we'll just make it 6. Let's make it 6 would have on 7. Okay, and then the bottom one we would just be 0.112 times 9.8. And we can run that real quick. That gives me 1.0976. Okay, and now we just go ahead and apply Newton's, or the summation of forces said equal to mass times acceleration, Newton's second law. And we would get, on this case, we'll get a negative 1.0976 plus F of 6 over 7 is equal to the mass 0.112 times the acceleration, and we were given the acceleration here as 2.85. And run the math on that. It's 1.0. And we get the F of 6 onto 7 is equal to 1.4168 newtons. Alright, so it's pushing up. Now what you would do now, you just do a free body diagram of C6. We come down here, I draw that, and now we will reverse this and go back the other way, and we'll make that 1.4168 newtons coming down. Now, also we've got to consider the mass of the object itself, the mass of the link, and we know from this problem that this has to be 1.0976. We'll have a force coming up. Again, we are doing 6, so this would be the force that 5 is having on 6. Again, do the same thing, summation of forces in y is equal to mass times acceleration, and we will get the summation of forces in y, we will get minus 1.0976 minus 1.4168 must equal to 0.1, excuse me, we left one off, plus the F of 5/6. All we have to do is set that equal to 0.112 times the acceleration of 2.85. We'll run that number real quick. So, and then move this here. I'll put the numbers down. That gives me minus 2.5144 plus F 5/6 is equal to and let me get that real quick. That was 0.112 times 2.85, and that's 0.3192. Move this to the other side, and we will get F 5/6 is equal to plus of 2.8336 newtons. And again, that's going back up. Okay, we'll do one more, and then I'll talk about a pattern that's developing very quickly. So now we go back and we'll do the free-body diagram of link number 5. When do link number 5, I'll have this going back down 2.8336 newtons. We'll have its mass times gravity coming back down, which in this case will be 1.0976. We will get the force that 4 is pulling onto 5. Again, that's our free body diagram. We go back to summation of forces in the y direction is equal to mass times acceleration. Summation of forces in the y direction in this case will be minus 1.0976 minus 2.8336 plus F of 4/5. And again, that must equal to 0.112 times 2.85. We'll simplify that real quick. That number there plus 1.0976. So on the left side, we'll get this value here of minus 3.9312 plus F4/5 is equal to 0.3192. So add that to the right side, and we'll get 4.2504 is going to be F4 onto 5. Now the thing to note here is there's a pattern being developed. We had 1.4168. We just doubled that. That gave me 2.8336. So look what's happened is we've added this again to this value here, which gives me the 4.2504. So every time you go up by a length, you will increase the force between them by this value here. Then again, you could draw free body diagrams all day long, working your way back up through these lengths, and you'll find out very quickly that that is what's taking place. So now if you want to find out what this force would be here, we can do that very quickly by looking at what's taking place here. So at 4.5, at this joint right here, we will get, write this down, 4.2504. And we're increasing each time by 1.4168. So all I need to do now is see how many links I'm going to jump up to. So if I go do this in blue, I will go 1, 2, 3, and then back to 4. So at this value right here, I should get 4.2504. Plus, we said we jumped 1, 2, 3, 4. And then number plus 4 times 1.4168 gives me a value of F is equal to 9.9176 newtons. Okay, now to prove that's correct, if you think about it, what is the total mass that you're trying to move? How many links you got? You got 1, 2, 3, 4, 5, 6, 7. Okay, now just draw a free body diagram of those 7 lengths, and what I will have, I've got a force coming down here. This value here is just going to be 7 times 0.112 times 9.8. Let's see what we get that. So if it takes 7 times 0.112 times 9.8, gives me a value of 7.6836 0.32 newtons coming down. Let me make that a little bit straighter here. Okay, we'll have a force coming back up, which you know that force has to be greater than that because we have acceleration. We go back to summation using Newton's law, summation of forces in the y must equal to mass times acceleration. We have the force F minus the 7.6832. All we have to do is set that equal to the total mass, which is 7 times 0.112 times the acceleration coming up, 2.85. All we have to do now is solve for F, and when we do, look what we get. F, move this to the other side, F is equal to 9.9176 newtons, and that's exactly the value I got here, so we know we're correct. Alright, so the chain problems are really not too bad. Again, the importance is drawing good free body diagrams to get the correct answer.